Hello and welcome to another episode of the BHS Science Lab. I'll be your host today, and today we're going to be working with Mr. DeVos. So what do you got for us?
Well, I have three things planned for us today. The first thing is something you can do at home, kind of an arts and crafts project. This is called flower chromatography. It can be done with coffee filters and markers. These markers that I'm using are Expo Vis-a-Vis wet erase markers, which means they're water soluble, which means the ink in these markers will separate out when introduced to water molecules based on their molecular geometries. The way that it works is you take a normal coffee filter. For this, I folded it up like a pizza, and I cut a design into the ends. When you unfold the coffee filter, you can take some of your favorite colors. But what we learn about colors is that this purple marker is actually made up of more than just purple. And if you remember your art class, black is made up of every color. And that's what Isaac Newton taught us about the spectrum. So I'm going to use black and purple only in this flower. And to make this flower, I'm going to put some black lines. And some purple squiggles.
Does the design matter?
Nope. I have students that like to do this. They try to write their names, they try to write their initials, or they try to draw a smiley face, and at the end, it all changes. So once you've put your design, remember I've only used purple and black. And later you'll see what kind of colors purple and black actually are made of because of the separation of the chromatography. This flower was made earlier. And you can see any of the original marks are basically gone. The yellows are actually green. The purple and black you see at the edge started out as black and changed from all the other colors. The colors are drawn out in the water. How it works is you take a second coffee filter and you roll it up into a stem, and you put the stem through the hole in the center of the flower. You're going to take the flower and you're going to set it in a small cup of water. The water will draw up through the stem and bleed out the colors. And we're going to come back to this later because it takes about 20 minutes in order for the colors to completely bleed out. We're going to stop here and go to a commercial while I set up the next step, which is called the Hindenburg.
Over 70% of people with learning disabilities are considered social outcasts.
Can you read that next section for us, please?
Like countless others,
Dyslexia is basically a difficulty in learning to read.
Haramus and the horrors.
Kids with dyslexia have the same feelings as you and I, which means you shouldn't treat them any different.
He witnessed while fighting.
Dyslexia can be overcome, and one day, people with dyslexia might just rule the world.
Do you know what drugs do to your brain? Do you know what drugs do to your body? There's all types of drugs out there.
Marijuana, cigarettes, pills.
Drugs cause extreme damage to your mind and body. The only way to stay free from the effects is to say no
to
drugs!
Be drug-free.
Hi guys, welcome back to the BHS Science Lab.
All right, now that we're back, after a couple setup changes, we're going to do it at a lab called the Hindenburg. Now, if anybody knows their history, the Hindenburg was a blimp. It came over from Germany, came through a storm across the Atlantic Ocean. Now, during a storm across the ocean, you have lightning, you have rain, and you have clouds. Well, all that adds up to a nice big static charge. We know now that the Hindenburg blimp, which is made up of aluminum, collected a static charges across the Atlantic. When it tried to land in Lakehurst, New Jersey, which is about 2 hours directly north of Bridgeton, and the original airfield that it landed at is still there. When a blimp comes into land, it drops a cord to the earth to dispense of the electrical charge that it gathered during any travel. Unfortunately for the passengers on the Hindenburg, a small tear had developed in the bladders of the blimp. Now, they used to use hydrogen. Hydrogen, we know, is a light gas and it floats in air. If you fill a balloon with hydrogen, it will float. However, hydrogen is extremely explosive. So, when the electric charge left the ground to balance out what was collected on the ship, that electric charge ignited the hydrogen in the Hindenburg. And all of its passengers, sadly, died in about 3 minutes. Because the explosion is so intense, they found the jewelry of the women that were on the Hindenburg fused together on their skeletons. That is how hot hydrogen and how fast it will burn. So we're going to create a mini Hindenburg today in 2 different setups. In this beaker, I have a product called zinc. It is the actual metal zinc right off the periodic table. In this beaker, I have something much more common. It's called sodium bicarbonate. In other words, baking soda. If you cook, you use baking soda. In this beaker, I have something called hydrochloric acid. If you've ever used Drano, you've used hydrochloric acid. Hydrochloric acid is an acid, but it is a mild acid. Your stomach needs hydrochloric acid. In this beaker is another very common thing, and you had told us earlier that it smells like, remember?
No.
It smells like vinegar.
Oh.
Because it is vinegar. I'm going to mix vinegar and baking soda. How many of you have done this before? Well, if you have, you'll know that it's that volcano trick where the bubbles come out and over. I don't want the bubbles to spill out and over. I want to collect them, and I want to see what's in them. So that's what I'm going to do with both of these. I want to collect the bubbles. Yes.
We'll be back. Commercial break. And we're back to where we left off.
All right, everyone, you saw that a large amount of gas was produced out of that. That was a gas that wasn't really great for us to breathe in, so we did take a break, ventilate the room, but we're right back where we left off. As you can see here, I've taped the 2 balloons up on the top of my fume hood. The purpose of a fume hood is it helps get the bad gases out of the classroom, and it gives us a little bit of light on our experiments. We're working just outside the fume hood right now. The pink balloon, if you'll remember, this was just the vinegar and baking soda. This makes a gas that we all require in our daily lives. This makes a gas called CO2. CO2 is not lighter than air, so it would sink. It would not make a very good blimp. But the bonus to CO2 is that CO2 is not flammable. In the orange balloon, we mixed hydrochloric acid with zinc. Now that gas that came out of there, that was hydrogen gas with a little bit of chlorine, which is why it's not so great for us to breathe in. But that hydrogen gas is extremely flammable. And what I'm going to demonstrate here for you on an extremely small scale is the difference of a non-flammable gas under pressure and a flammable gas under pressure. Non-flammable, flammable. Not very exciting. the non-flammable gas actually will extinguish my lighter flame. The balloon is still here, and there's nothing left inside. Let's go to the flammable gas, which is under pressure. Any kind of a balloon is under pressure. Now imagine that in about 3,000 gallons above your head. All of a sudden, poof. When fire is above your head and falling on you, it's not a good day. That's the lesson we learned from the Hindenburg. When you see the Goodyear blimp flying above your favorite football game, that's filled with helium now. Helium, not explosive, not reactive. And any chemistry student will tell you that helium is a noble gas, and that's why we like it. Okay, we're going to take a break now, and I'm going to set up my last experiment, which is called the dehydration of sugar. You can't try this one at home, though. This one is also very dangerous.
It doesn't matter.
Stop. That water bottle can spend hundreds of years in landfill. Americans use 2.5 million water bottles every hour, and most are thrown away. If we save just 1 ton of plastic, we can save 1,000 to 2,000 gallons of gas. So just think about it.
Reduce, reuse, recycle.
Hi, and welcome back to our third experiment.
All right, everybody, this one is going to be the dehydration of sugar. And in order to understand exactly what's going to happen, we have to have a mini chemistry lesson. This is sugar, C12H22O11. In other words, I have 12 carbons, 22 hydrogens, and 11 oxygens. What that really means is I have some pure carbon and some hydrated compound, which means it has water in it. Whenever something is said to be hydrated, that means we have some water in it in a molecular format that can be removed if we have to. Whenever your body is dehydrated, you have to drink a glass of water to get it back. In the opposite case, we can rapidly dehydrate something. And if you like dried fruit, you've eaten a dehydrated fruit. All right, to understand how do we dehydrate sugar, is that I'm going to use a very, very strong chemical called sulfuric acid. This is something that you don't want at home. This can eat through my clothing, it can eat through my skin, it can cause a burn. Whenever someone hears burn, they think fire. A chemical burn is much worse, because I just can't put this out. So I want to be very, very careful. Whenever you're handling chemicals like this, you want to make sure you have all kinds of safety gear on. I'm going to pour the chemical, the sulfuric acid, into the sugar. When I do this, a reaction is going to take place. Now, it's not going to look like much at first. It's going to start to turn brown, and it might bubble, and it might start to smell funny. But as soon as it starts to smell funny, I have to put it back into my chemical hood. And I'm going to use this as a safety precaution. Once it's in the hood, we can get close to it and watch it through the protective glass. We're going to remove all of the water from the sugar. It's a process called dehydration, but really the water is evaporating very, very quickly. And if I look at my chemical formula again, I can see that if the water goes away, the only thing I have left is carbon. Carbon is an element, which means it's in its absolute purest form. If anybody can think of what carbon might look like in its purest form, some people might say it looks like a diamond, which is true. It looks like that stuff that you use when your pencil, which we call lead, which is not lead anymore. Modern pencils are made of graphite, which is carbon. It also might be what's left over at the bottom of your campfire in the form of ashes. So depending on what your vision of carbon is, you're going to either see if you were right or wrong at the end of this experiment. All right, adding the strong sulfuric acid to the sugar. I'm going to stir it a little bit. Okay. You can see a chemical change. If you're standing close, you might be able to hear a change. You can start hearing some bubbling. But we're going to watch it for a moment on the table. But as soon as we see a strong chemical reaction, I have to put it in my hood. I'm going to turn my fan on. The lights are on. We're going to be able to see what happens. And already there's something is happening in there.
Looks like soda, actually.
It is. It's starting to look like a Diet Coke. You don't want to drink this, though. All right, at this time I am going to move it over to the hood. We're going to watch it from there. Now I'm going to step back so everyone can get a good view. Well, I think my new friend has stopped growing, so we're going to take him out of his beaker. And there we have a carbon stick. This is all that's left of that sugar. Now it's also very hot. You can see the steam is coming off of it. And my camera crew here and my host can definitely smell there's a very bad odor. This isn't very good right now. This still contains a large amount of acid. The only way to make an acid go away is to do a process called neutralization. In this bucket I have some water and some of that sodium bicarbonate I spoke of earlier, which we know as baking soda. So I'm going to dunk my new carbon into the baking soda. Now it's probably going to fall apart as some of the bonds will break down, but I want you to notice what else happens. Ooh. Bad smells. Okay. Now that it has been neutralized, and this could probably sit in here for a couple hours and still neutralize, but at this point, it's safe enough for me to hold and touch. There we have, and I'm just going to break off a small piece so I can show everybody. This is our sugar that we started with. All the water went away, all the hydrogen, all the oxygen, and all I have left is carbon. Now my advice is, if you can get a hold of some sulfuric acid and get a hold of some sugar, mix it together, do what I did, neutralize it, bury it in your backyard, wait about 5,000 years and you have a nice diamond ring to give to somebody. This is carbon. The only thing separating this from a diamond is time and temperature. If you're into jewelry, you'll know that there is a synthetic diamond on the market. A synthetic diamond is made exactly how what you see I'm doing here, except in very proper format, in a big lab, in pressure. That's all I have for everyone today. I hope you enjoyed our show. I'm going to turn it back to the host for a quick wrap-up. I've been Mr. DeRose. Have a good day.
I'm Veronica Lorata. See you next time.